Good morning, everyone. My name's Alice Price, and I typically teach calculus all day, but my AP calculus classes have tons of fantastic problems. Thank you, College Board. So I decided to focus on Calc 3 because my Calc 3 class, even though it's high level, the problems that are being solved could use a bit of amping up. So that's where I'm focusing today. So we're going to start with part one of Polya's four-step process here, which is understanding the problem. And my approach is going to be to read the problem, sketch any relevant pictures, and act out the problem. And then we'll dive into making a plan. Normally with my students, they would do similar things, but then there would also be a lot of discussion involved. It's hard in a video that you can't have discussion when you're just by yourself, which I think is a shame because I think that's such a huge part of understanding the problem. But we're just going to make do with what we've got. So let's begin. All right, I'm going to read this fairly quickly because it is a big problem. Oh, by the way, just to mention, where did I get this problem? I got this problem off of a site called brilliant.org. And if you haven't been on the site, it's a great site. Tons of great activities, problems, lessons. I actually had to stop getting their daily emails because I was spending so much of my time each day solving their problems and not focusing on my lesson planning. So I had to stop their daily emails. But they are a lot of fun, very challenging, and actually, I think really fitting to what we are doing. Let me make this a bit bigger. All right. A toy car is placed in the XY plane at the coordinates 0, 6. It faces the point 310 and is programmed to travel in a straight line in the direction of that point. If the height of the surface it travels through is modeled by the function f of xy equals y sine pi x over 2 plus 2x cosine pi y over 2, and the car travels at a constant speed of 10 units per second through the xy plane, calculate the slope of the surface where the car is at after 2 seconds. I should mention what my students would and would not have seen based on this problem. So my students would have just finished up a unit where they were doing some motion problems. So they would have done motion problems in the past involving parametric equations. In the current unit, they would have learned concepts like gradient and concepts like directional derivative, but they would not have done any applications yet, just simple exercises. And they would certainly never have linked directional derivatives to a motion problem. All right, so we've read the problem. To draw some relevant pictures. So if I were a student and I was looking at this, I might go ahead and just sketch a quick XY plane, put a point at 0, 6, and then put a point roughly at 310. And then, sketch kind of a path right there. So we're starting at 0, 6, and we're traveling in the direction of the point 310. So I've got a picture of my straight line path, but now I have to deal with this surface. So another strategy that we can use just to understand the problem is to get a visual of what does this surface look like. And so in order to do that, we're going to need some 3D graphing software. GeoGebra works just fine. I personally, I work in a district where every single student has a MacBook, which is really nice. And so because of that, we all come with pre-installed software called Grapher, which is my favorite graphing software. Really easy to use for 3 dimensions. So I'm going to go ahead and open up a new graph in 3D, and then I'm going to type in my equation, which is y times the sine of pi x over 2 plus 2x times the cosine of pi y over 2. All right, now when I hit enter, it looks like this, which is really crazy. And my students are pretty used to seeing graphs that look like this. The first thing that I do is I have to turn off this checkerboard. It's so distracting to me. So I'm going to click up here, turn off my checkerboard, and just pick a color that I can see easily. All right. So now we've got this crazy looking thing, and I don't know if I can see where the car is traveling. It's even hard just to find the axes, right? So my Z is always pointing up. There's my X, there's my Y. So if I zoom, let's see what happens if we zoom in. First, let's zoom out just for giggles. Whoa, right? Okay. So zooming out really doesn't help us at all. This car is going to have an insanely hilly path. Look at that. It's quite spiky. Um, so that it could be, let's just zoom in and just see what happens. Just see if I can make it a little, there we go. Okay, so zooming in makes it a little bit easier to manage. So it's just so you can kind of tell. So here's our X, here's our Y, there's the Z. So here's the origin. We're starting at, oh gosh, the point, I think 0, 6. So we're starting over here, and then we are traveling in the first quadrant this way. So what ends up happening is we're probably going to go, if you can tell, there's kind of a hill. We're going to go up a hill and we're going to go down a hill. Later on in this graph, we would probably go back up again and go back down again as we travel in this straight line following the path that was outlined. So this is kind of a picture of what the surface is going to look like. It really doesn't help us solve the problem, but it is kind of nice sometimes to get a visual and just be able to discuss what is going on. What does this situation look like? So to demonstrate how to act this problem out, I don't normally do a lot of visuals with objects, but now's the time to start. So what I'm going to do first is just create kind of an X, Y, Z set of axes. I don't have any dowels with me, but you know what? I thought yardsticks might be really good because they're pre-labeled, right? And so it's almost like you have your coordinates just labeled on your X and Y axes. And then if I added a third yardstick here to create my Z axis, now I've got a nice first octant to take a look at, but I'm not going to stand here and hold the Z axis. So we're just going to deal with the X and Y axes, knowing that the Z axis would be there. All right, so now I've got my toy car here, and it's going to start at 0, 6, and it's heading towards 3, 10, so it's kind of going like that, boom, right, like that. And so if the students were acting this out and just kind of modeling the direction of the car, which is traveling in a straight line looking down from the XY onto the XY plane, so they might think, well, let's see, maybe we need to find the slope of this line. Maybe we need to find the angle that this line makes with the x-axis, something like that. But it would be helpful if we could model our surface. Modeling a surface with objects is not easy, but I thought of possibly just using something like some bowls. So I just grabbed some bowls. I'm going to move my axis out of the way here, and I'm going to try to pull a sheet, just an old sheet, over these bowls. And then what's happening is that now I have kind of a surface with like some hills and valleys and stuff, and I'm going to put my axes back. All right, so there's an x-axis. Okay. There's a y-axis. All right, not perfect, but you know what? It's good enough. Okay, so, whoops, I gotta turn my y-axis around. Okay, so now I've got some sort of a surface. I have no idea what the actual surface looks like. This is just kind of a guess that I'm gonna play with my car here. So as my car is traveling in a straight line, it actually is going to kind of go up and it's going to go down. It might hit some hills, it might hit some valleys. And so what we're finding out is we're finding out how steep is the hill that the car is traveling on at some point along this line. And we don't know what that point is yet. We don't know the equation of the line yet. Not hard to find. That part's not bad. But just to understand the problem, what we're trying to do is trying to find how steep is this hill. And in our terms of what we know, that would mean we're looking for really the rate of change of z with respect to how far we are traveling in this direction. So we've learned that our partial derivative with respect to x gives us the rate of change of z in the x direction, and with respect to y gives us the rate of change of z in the y direction. So what we're going to probably need to use is a directional derivative in order to get the rate of change of z in the direction that we want. So after looking at the sketch of the surface and modeling it with our toy car, I think we at least understand now that even though it says straight line, and it is a straight line if we look at it top down, if we are looking at this car kind of from the side, it's actually traveling kind of on a hilly road. And so we've got this car that's kind of moving along these hills, and what we're trying to find is the slope of the surface. So we're trying to find how steep is this slope. Here, it could be here, it could be here. Wherever the car is after 2 seconds, how steep is the hill that it's on? Okay, so let's go ahead and make our plan. So part 2 is to devise a plan. And for this problem, I think the most relevant methods that we're going to use is to look for a pattern, which in this case, when we look for patterns, and patterns can mean so many different things, looking for a pattern to me in this problem means, do I see something that I have seen before? So I think more like relating prior knowledge. And then, is there a simpler problem? Is there part of the problem that I know how to do, even if I might not know how to do the whole thing? So that's going to be our plan, looking for a pattern and seeing if there is a simpler problem. So when we take a look at this problem and we look for a pattern, and I'm going to do this from a student perspective, there are a couple things that might jump out that we have seen before. One of the things that we would have studied in the past is speed. And so we do a little time with motion when we are studying vector valued problems. So I would think if I was a student, I might see that word speed and think, all right, I think maybe I should go down the path of calculating the speed. So let's see. So I'm going to say for our plan for step 1, we're going to see if we can write a vector valued function for our path, right? A path function, and then use that function to find the speed, find a speed function, and then set it equal to 10 and see what that yields for us, right? So we'll see. If I was a student, that might be one attempt I would go through. Another thing that I would recognize is slope of the surface. So when I see slope of a surface, we have learned slopes in a couple different perspectives. So we have learned partial derivatives. So a partial derivative with respect to x will give us the slope in the x direction. And with respect to y would give us the slope in the y direction. But it sounds like we don't want a slope in x or y. We want a slope along this line. So that means we're going to need to use a directional derivative. All right, so I think our plan is to do those two things. All right, so our next step is to carry out the plan. We're going to try a bit of guess and check as we work through our plan and see what works and what might not work, and then we might back up and try a different path. So let's give it a shot. So we're going to start by focusing on that speed. And if I start by resketching my path here, so I have a point 0.6 and I have a point 3.10, and I'm going this way. So the first thing I might want to do is find the equation of this line, right? So we have y equals, slope of this line is 4/3 x, and it's been shifted up 6. So there's our equation of our line. So if I wanted to write a parametric equation of this line just in the xy plane, I could write r of t, let x equal rt, and then just set y equal to 4/3 t plus 6. Okay, so perfectly defined path function. So now if I wanted a velocity function, I could say r prime, and so I'd do our derivative with respect to t, so I'd get 1 and 4/3. And as a student, I know that speed is the magnitude of the velocity, so I would go with the square root of 1 plus 16/9. All right, whoops, there we go. Okay, let's see. So we get square root of 25/9, which is 5/3. But now I look at this and I think, okay, we have a constant speed of 10. How is this possible? So I'm thinking I have hit a snag. So I'm going to kind of abandon this and go with a different approach. So the second thing in our plan was to take a look at the directional derivative. So I'm gonna switch back to my plan and try just finding the directional derivative and see what that gives. All right, so when we're finding the directional derivative, the first thing we need to find is the gradient of the function. So I'm going to go ahead and find the gradient of f. And so we have, if we do partial x, so we're going to have pi halves y times the cosine of pi x over 2, and then plus 2 times the cosine of pi y over 2. Okay, and then for our y-coordinate, we would just have the sine of pi x over 2, and then we would have, when we do the derivative of cosine, it's going to be negative, so I'm going to put a negative there. So we would have pi halves times 2x, so we end up with just pi x times the sine of pi y over 2. Okay, and that might take students a little while to just kind of wrestle with all the trig and a little bit of chain rule in there, but I think they'd be fine. So we find our gradient. Now we need to find a direction vector. So our direction vector is going to be the vector that passes through the points 0, 6, and 310. 0, 6, and 310. So I'm going to call it U. So our direction vector would just be, we'd be going 3, that's a 10, sorry, and then 4. So our direction vector would be 3, 4. Okay, but in order to find the directional derivative, we need this direction vector to be a unit vector. I'm going to quickly just point something out here. With our 2 points, sometimes there's a reason when sides are 3 and 4, right? So kind of nice that we know that our magnitude of our vector is 5. So we end up with a unit vector of 3/5 and 4/5 because the magnitude of that vector is 5. All right, so now let's go and find our directional derivative. So I'm going to call it d sub u of f. And if we do the dot product of our gradient and our unit vector, direction vector, so we would get 3/5 times pi halves y. So you end up with 3 pi y over 10 cosine pi x over 2 plus 6/5 cosine pi y over 2. Oh, draw my parentheses there. All right, plus 4/5 sine pi x over 2 minus 4/5 pi x sine pi y over 2. All right, so we've got our directional derivative. So, well, let's see. That's great, but now we still need to know what x and what y to plug in. So using the speed by finding a path and differentiating did not pan out. So maybe we need to think about this in a simpler way. So I'm going to go to the next screen and just write this out one more time. So something that struck me when we were finding our unit vector, so this is 0, 6, 3, 10. So we had a 3, 4, 5 triangle. And one of the things I noticed is we have a constant speed of 10 units per second. When we travel from 0, 6 to 310, we've traveled 5 units, right? So if we were to do something similar, another 5 units, we'd have traveled for 1 second. We want to travel for 2 seconds, so we need to actually travel a total of 20 units. So really all we need to do is find this coordinate right here after we've traveled kind of these like 4 little sets of 5, right? So what would be the coordinates? Well, we would have in the x value, we'd have 4 3s as we go over, so we're going to land at 12. And then for our y value, we'd have 4 4s, so we'd land at 16, except we started at 6, so we got to shift ourselves up. So we're going to land at the coordinate 12, 22. And we found our x and y values to plug into our directional derivative. So if we back up to our directional derivative, looks like now we can go ahead and plug in our 12, 22. That's a D, it just came out bad. Okay. All right, so if we plug in a 22 for y, we get 66 tenths or 33 fifths pi times the cosine of 12 pi over 2 or 6 pi. So that lands us back at the origin where the cosine is just 1. All right, so then we get 6 fifths times the cosine of 22 pi over 2 or 11 pi, which lands us over at pi where the cosine is -1. All right, if we plug in a 12 for x into our sine function, we get the sine of 6 pi, which is 0. And then if we plug a 22 in for y into our second function, we get sine of 11 pi, which is also 0. So it looks like our directional derivative is going to be 33 pi fifths minus 6, oh, that didn't turn out, 6 fifths. So, or we could kind of pull out a 3 fifths here and then do 11 pi minus 2. Okay, so we have essentially solved the problem. Let's kind of look back for a minute and think about what did we actually figure out here, right? So we just found the slope of the surface was 3 fifths times 11, what did I get? 11 pi minus 2? Yeah, 11 pi minus 2. So what does that tell us? Well, when the car is driving, this is obviously going to be a big positive number, right? It's around, it's something higher than 30. So, times 3 fifths. So something in the 20s or 30s. So either way, it's going to be a big positive number, which means our car is going to be going up. It's going uphill and it's going to be a fairly steep hill, right? So certainly higher than 45 degrees. So we've got a car that's on a very steep hill traveling up. We don't know where it is in proportion or in relation to the top of the hill or the bottom of the hill before, but we do know that it's going up and it's traveling at a fairly steep point. All right, if we wanted to find the steepest point, we know we could use the gradient, but we're not going to get into that right now. All right, so let's think about what else. So walk through the process. We started by taking a look at the speed. That did not pan out. So we instead focused on our surface equation and finding the slope of the surface using the directional derivative. That worked well. The only part where we hit a little snag was coming up with figuring out the location of the car after 2 seconds, which actually just involved a little bit of simple math. Sometimes in Calc 3, we are so focused on our calculus that we tend to overcomplicate things, and we forget that sometimes things can be made a bit simpler. So we found that, and we were able to apply that to our directional derivative to find our final slope of the surface. So I would say overall we did fairly well. So we hit a couple snags with finding the speed, but overall I would say we did good. What worked, what didn't? Well, the best thing that worked was doing what we knew. So we knew slope of the surface meant directional derivative, and so or gradient. Or partial derivative. But we knew that since we were not going along an axis, that we were going to have to do a directional derivative. So going with what we know really worked well. Relating to prior knowledge as far as directional derivatives go worked great. But the speed was our little snag, but we got past it and all was good. Thank you so much for watching, and I hope you all have a great day.